Welcome back, ladies and gentlemen. In this video, what I would like to do is some review of kinematics and also related to Newton's second law. Specifically, the kinematics is going to focus on graphs, and I'm hoping this will be helpful to at least some of you, if not all of you. So here we go. There we go. Trying to make it quick and do a slide change. So here we are looking at a position time graph. See the position in the x direction and units of feet and time. So position time measured in seconds. You can see it's fairly linear. Cool. We applied a linear fit. Now I want to point out first that the data isn't linear because we applied a linear fit. This description here is for the trend line that we added. It is not for the data. When we apply this linear fit, we're simply judging the data to be linear. But it's a decision we've made. It's not what the software is telling us. It's not what the program is telling us. So I just want to make that clear. Okay, but what are we looking at? So if it's linear, we have a slope to the line. And you can see here in the data information box, it says m is slope. So this equation here, x equals mt plus b, that should sound a little familiar. That might be similar to y equals mx plus b. But here in the video today, I'm not really going to dive into why it's an x instead of a y and why it's a t instead of an x. Okay, but m is the slope of a line in the general form of an equation for a line on a graph. And here it's telling us the slope is 1.616, and then plus or minus, and then this small number, and then feet per second. All right. So what is the value of the slope of this line? Well, the value of the slope of this line is the 1.616 feet per second. The plus or minus is an uncertainty in that value, but that right there is the value, 1.616 feet per second. So there's units that go with the number. I'll make that clear. So now, what does the slope of a position time graph represent? Again, focus on the fact that this is a position time graph, a PT graph. The units are a clue. These units are feet per second. Now, you might have units of centimeters per second, meters per second, miles per hour. It sort of doesn't matter. If it's some sort of distance divided by some sort of time, then what you have is a slope that represents a velocity. Cool. The value is the number plus its units. But what it represents, its meaning, is that that is a velocity. What does it mean that it's linear? Well, if it's linear, the slope is constant all the way up. It's the same slope all the way up. What that means, since it's a velocity, that the velocity is constant for the whole time. Cool. So that's what that indicates. With a constant velocity, the acceleration would be zero. And in order to get zero acceleration, there must be zero net force in the x direction, whichever way the x direction is. If it's horizontal, then that'd be zero net force in the horizontal direction. Okay, cool. So there's your connections. All right, but what if the position time graph is curved? Well, check this out. Since the slope of the line, you can see the line is curving, and since the slope represents velocity, well, the slope here is changing, right? So you look at this, you know, the slope down here is pretty small. It is an upward slope, but it's not very big. The slope up here is much steeper. So the slope has changed. Cool. Well, if the slope is changing, there's a change in velocity, and that means there must be an acceleration. And if there's an acceleration happening in that direction, there must be an unbalanced force in that direction. So there's some sort of net force. So this is what we can conclude, even if we just see this. Any kind of curved position time graph. There's an acceleration, and therefore there's an unbalanced force. There's a net force acting on it. Sweet. All right. Well, what might the various forms of position time graphs look like? Check this out. Clearly, in all four of these graphs, we can see the slope is changing. The lines are curved. And so in all four of these graphs, there will be an acceleration. So the velocity will be changing. But what does it mean? How do you interpret this? Okay, well, if you look at these first two graphs, they both show that the object is speeding up. This one, the velocity is small in the beginning and fast at the end. But it's positive. The slopes are positive here. In this one, the velocity is small, the slope is small, and later on the slope gets steeper, so it is going slower and then faster. It's speeding up, but the slopes are negative. Well, but in both cases, it's speeding up. In the first case, it's moving in the positive direction, and the second case, it's moving in the negative direction. All right, well, that is just the opposite here. For these two graphs, the object is slowing down. How does that work? You look at the slope in the beginning, it's very steep, and it's also very steep here. It's just steep positive slope and steep negative slope. And since slope is velocity, that's a positive velocity moving in the positive direction. That's a negative velocity moving in the negative direction. But it's moving fast in the beginning in both cases. Later on, after more time has gone by, the slope is much smaller. So the object is moving slower. Same thing here. After more time goes by, right about here, the slope is much less steep. Sometimes called a shallower slope. So it has slowed down. So in both cases, slowing down. Cool. I want to look at these same graphs again, but they're organized a little differently this time. And I want to focus on something else because you might encounter some descriptive words that describe the lines that some students may not have heard of before. And the words are like concave up or open up. And so I want to show that to you. These two graphs show a shape that is open up, in other words, concave up. And what that tells us is that the acceleration is positive. And the way I learned concave up or open up is that, imagine, the word concave is kind of like a cave, and the opening is up. Cave opening is up in both cases. Never mind, that's a little to the left here, a little to the right there. It's generally upward in both cases. Cool. Well, what that means is the acceleration is positive. I'll come back to this idea in a second. For these two, you can see that the cave is open, aimed more down instead of up. So these would be open down or concave down. And this means the acceleration is negative. So you can just look at the way it's curved, open up or open down, and you can tell which way the acceleration is. Now, this is very important. It's true that in both these first two graphs, the acceleration is positive. That does not mean that the object is speeding up in both of these cases. In this case, in the first case right here, the object is speeding up, the slope gets steeper. But in this case, the object is slowing down. The slope gets smaller value slope, is slowing down. And that's true for both, even though, I should say, that they both have a positive acceleration. One of them is speeding up and the other is slowing down. And the reason that can be is, well, this one's moving in the negative direction and has a positive acceleration. So that'll cause it to slow down. This is moving in the positive direction and has a positive acceleration. That'll cause it to speed up. Okay, and the reverse is true for open down or concave down, right? This one starts out fast in the beginning and is slowing down. But the slopes are positive. This is like, up and to the right. This is still up and to the right. It's a positive slope. But the acceleration is negative. So moving in the positive direction with a negative acceleration, it's going to slow down. Here on this one, the slopes are negative. It starts out with a small slope, moving slope, and the slope increases, so it's speeding up. But the slopes are negative, so it's moving in the negative direction. Moving in the negative direction with a negative acceleration, it'll be speeding up. It makes sense. All right, just a little bit more here. Yeah, speeding up, slowing down, speeding up. Slowing down and speeding up. Cool. Okay, so finally, I want to move on to velocity time graphs, and here we have an example of a velocity time graph. In general, we are only going to deal with velocity time graphs that are linear, so we don't have to worry about curved velocity time graphs. If we do see a curved velocity time graph, that means the acceleration is not constant. So I'll get to that right away. For a velocity time graph, the slope of the line has some value to it, some number. Remember, the value just means the number plus its units. And I don't know, this might be like the value of 5, who knows? But the units would be meters per second squared. That's the units of acceleration. All right. But what does the slope represent? Well, since it's got the units of meters per second squared, and the velocity is changing in all likelihood, depending on the line, the slope represents acceleration. So the steeper the slope, the greater the acceleration. Cool. Now, if you have an acceleration, if the line has a slope, and in this case, the slope is positive, right? Well, then we have a positive acceleration. And that means in that direction, whatever direction we're dealing with, then there would be a net force in that direction to cause that acceleration. So let me show another graph and just explain that. So here we see three different lines. The blue line has a positive slope, so it will be showing a positive acceleration, and therefore there is a net force acting in the positive direction for this line. The red line has a negative slope, and so it's indicating a negative acceleration, and that means in whatever direction we're looking at, there will be an acceleration in the negative direction, and therefore a net force acting in the negative direction. The black line, well, it looks like a zero slope, so it's showing zero acceleration, and therefore in whatever direction we're analyzing, there would be no net force acting in that direction. And no net force could be either no forces at all in that direction, or it could be just that the forces that are in that direction are canceling out. They're summing up to zero. One might be positive, one might be negative, and so they end up adding together and canceling out. Okay, so positive slope, positive acceleration, and net force in the positive direction. Negative slope, negative acceleration, and net force in the negative direction. Zero slope, zero acceleration, and zero net force. Cool. Well, there's one more possibility that's only like 1/2 a step more complex. What if you have a graph like this? So pay attention to the slope, of course. So we said negative slope, so negative acceleration, and it's a negative slope the whole way down. That means there's a net force acting in the negative direction for the whole time period. Okay, cool. But where is the line in the beginning? Up here, we see the line is in the positive region of the velocity axis. So it's moving in the positive direction up here. Down here, it's in the negative region of the velocity axis, and so it's moving in the negative direction. So what does that tell us? It went from moving in the positive direction and then crossed this line, and now it's moving in the negative direction. That means it must have changed directions. It was moving in one way, and then it's moving the opposite way. Well, what happened right here when it crossed that horizontal axis? What happened there is at that moment, that exact time, the velocity was zero. So it wasn't moving. This is where it turned around. This is the turnaround point, so to speak. All right, so we can also say, well, we know it had positive velocity in the beginning, but a negative acceleration, negative slope. And so it had to be slowing down. And that makes sense because it was headed toward a zero velocity right here. And then from that point, it had negative velocities and negative acceleration. So it would have been speeding up, which makes sense. It's getting further and further away from the zero velocity and getting faster and faster in the negative direction. Cool. And again, the slope of the line just means you can find the value of that acceleration by looking at the slope of the line. Sweet. All right. That is exactly what I wanted to show you. Thanks for watching. Catch you next time.